Alright, in the previous lecture we talked about internal forces, especially about the internal forces that occur or that are induced in a beam due to applied external forces. We'll extend the discussion further and we'll talk about the calculation of those internal forces. We'll gradually move towards that, but before we do, we need to know or understand a few more topics. So let's start with the reactions or the support reactions. One thing that you need to know is that you don't always have to calculate the reactions, but even if you don't, calculating the reactions is always a good deal. Sometimes it would help you in validating your calculations, so it's a good way to see whether you're going in the right direction or not. And in some cases you need to calculate at least one of the reactions. You have to apply rigid body mechanics to find out the reactions. Now if you have gone through the basics of mechanics, you know that there are two major cases that we have gone through, or most mechanics books discuss in the beginning. There is this particle mechanics, which do not consider the dimensions of an object. So since the dimensions are almost negligible, the moment equation is gone. And then we have rigid body mechanics, where we consider the object to be non-deformable, but the dimensions are considered, so the equation for moment comes into the picture. So we'd be applying the rigid body mechanics instead of the particle mechanics. So according to rigid body mechanics, for a 2D object or in a plane, you have three equations: summation fx equals to 0, or summation of all forces along x-axis is 0, summation of forces along y-axis is 0, and summation of moment is 0. Now once you have calculated the reactions using these three equations, you'll move on to the next step, which is the determination of internal forces for each given section. You'll get to know about that in a while. Once a section is cut, the internal forces of the structural members get exposed, and again, like we have discussed in the previous lecture, those forces are axial force, shear force, and bending moment. Now the same equations of equilibrium that we have used in the previous step for calculating reactions, the same would be used now for each section to come up with the equations for the axial force, the shear force, and the bending moment. Again, these are the same equations, but the Fx equation would be used to determine the axial force equation, Fy equation would be used for shear force, and summation moment equation would be used to determine the bending moment. Once you're done with all of the sections, the three equations for each section, you will draw the shear force and bending moment diagrams. Now these diagrams are actually a representative of the shear force or the bending moment, depending on the diagram you're talking about, over the entire length of the beam. So they're a good representative of what's happening inside the beam in terms of shear force or the bending moment. And these diagrams would help you out in finding out the values of shear force and bending moment at critical locations, or the maximum shear in the bending moment and the minimum shear in the bending moment, which would later on help you in designing a beam to resist a given amount of force. Now one of the very important things that you need to do while you're solving for a beam is to mark the limits for each section. When you're cutting a beam, the length of that beam is taken as a variable x. Excuse me, I am actually suffering from a bit of cough, so you'll have to bear with me. Anyway, when the section is cut, the length of the beam is taken in terms of x, and it's always better to chalk out the range of x for each section. What you do is you'll mark the distance from extreme left end. Usually we do it from the left side, although I don't see any harm in doing it from the right side, but most of the world does it from the left side, so that's how we're gonna do. I'll show how this is done, and these distances will be taken as the limits for the respective sections. So if you see this diagram as discussed in point 3 as well, the extreme left, that is A, I've taken that as 0, and if I add the distance of the first force that appears after point A, that distance is 3, the distance between A and the next force is 3. So if I add that 3 with the 0, this 0 is the lower limit for the first section, and if I add this 3, I'll get the upper limit for this first section. So the limits for the first section are 0 and 3. If I add this 3 to the 0, I'll get the upper limit for the first section. Now for the second section, the lower limit would be what was the upper limit for the first section. The same number becomes the lower limit for the second section that starts right after this force. So this is the lower limit 3, and if I add the distance up to the next force, this is this 3 to the lower limit, I'll get the upper limit for the second section, which is 6. So the lower limit is the same as the upper limit for the previous section, so this goes here, and when I add this 3, this distance that is for the next force, into this lower limit, I get the upper limit for the second section. Now again, this 6 becomes the lower limit for the third section, and if I add the distance of the next force or the support or the reactive force, that's what do we have in this case, which is 4. If we add this 4 to the 6, we are going to get 10, which is the upper limit for the third section. So I'll go again quickly. You start from the extreme left, and extreme left would be taken as 0, and if you take the distance for the next force and add this to the lower limit, you'll get the upper limit for the first section. So the limits for the first section are 0 to 3, and for the second section, this upper limit becomes the lower limit for the next section. So this is 3, the lower limit. If you add this 3, the distance up to the next force, that becomes 6, which is the upper limit for this second section. Now again, this 6 goes here as the lower limit, and if you add the distance up to the next reactive force, it could be the applied force or reactive force, whatever is there. If you add this 4 to the 6, the lower limit, you'll get this upper limit. This is one of the easier ways that I feel this is very easy to mark limits. Otherwise, I have seen students struggling with the marking of the limits. This is just kind of a meme that we had in the classroom. This is if you have seen the movie, you must get the reference, you know, the movie taken the first part. Anyway, like I've said, it's interesting to note that the lower limit of a given section becomes the upper limit for the next section, and so 0 to 3, 3 to 6, 6 to 10, these are the limits. And again, you have to remember that the region under consideration is marked as X. It starts from the extreme left, extreme end, and goes to the point where the section is being cut. We'll show you through an example. This is the example that we're going to solve. I'll stop lecture 2 here, and we'll start with the example in the next clip.